You know, it's funny. We spend so much time and energy developing incredible new technologies, but so often nature already has the blueprint. Here's what most people don't realize. Sometimes the most revolutionary ideas aren't found in a high-tech lab. They're found in the most extreme, unexpected corners of our planet, hiding in plain sight. And today, we're diving into one of those secrets, a tiny marvel of engineering that could fundamentally change the way we cool our world.
So, to find this secret, our story has to start in one of the harshest places on Earth, a place that really tests the absolute limits of what it means to be alive. I want you to really picture this: the Sahara Desert. The sun is just relentless. We're talking about an environment so punishing that for most living things, survival isn't measured in days or hours, it's measured in minutes. Now, just let that number sink in for a second. 70 degrees Celsius. That's 158 degrees Fahrenheit. The sand is literally hot enough to cook on. This is way beyond an uncomfortable summer day. This is an absolutely lethal environment. But this is where the story gets really interesting. Because against all odds, one tiny creature has made this furnace its home. Meet the Saharan silver ant. And it doesn't just survive here, it thrives. It actually comes out to scavenge for food at the peak of the heat, right when it's so intense that all of its predators have been forced to go and hide. So that's the big question, right? How on earth does it do it? What kind of incredible evolutionary superpower does this little ant have that lets it walk this thermal tightrope right on the very edge of what's physically possible for life? Well, when scientists took a closer look, the answer they found was nothing short of a masterpiece of natural engineering. It turns out the ant was using this brilliant two-part strategy to stay cool. And this is a perfect example of what we call biomimicry. It's this idea that instead of inventing from scratch, we look to nature for inspiration, for solutions that have already been tested and perfected over millions of years of evolution. See, the ant's defense against this insane heat isn't just some simple shield. No, it's an active, sophisticated, two-part cooling system that's built right into the very hairs that give the silver ant its name. Okay, this breaks it down perfectly. These hairs have this really unique triangular shape, and they do two incredible things at the exact same time. First, they act like a tiny, perfect mirror. They reflect most of the sun's incoming energy, the visible and near-infrared light, right back out before it ever hits the ant's body. But second, and this is the really genius part, those same hairs are also hyper-efficient at taking the ant's own body heat and radiating it away as thermal energy. They're basically pushing its excess heat out into the atmosphere. And what's the result of this amazing dual-action system? Well, it keeps the ant's internal body temperature a full 2 degrees Celsius cooler than it would be otherwise. Now that might not sound like a lot, but in an environment where every single fraction of a degree matters, that 2 degrees is the difference between life and death. So we have this incredible biological solution that nature came up with. And this is where the story pivots from the natural world right into the world of human innovation. Because researchers looked at this tiny ant, and they didn't just see a cool bug. They saw a blueprint. They realized this ant was holding the key to a technology that could help us solve one of our biggest challenges: how to keep our buildings and cities cool without burning massive amounts of energy to do it. The technology is called passive daytime radiative cooling, or PDRC. Now, the most important word there is passive. What does that mean? It means this process can cool a surface even when it's sitting under direct blazing sunlight with absolutely zero energy input. It's cooling that works for free. And this chart shows you exactly how it works. It's a near-perfect copy of the ant's strategy. So, see that big yellow area? That's the material reflecting almost all of the sun's energy away. But at the same time, look at that blue area. That's the material radiating its own heat out, specifically in a wavelength that slips right through our atmosphere. It's like an open window to the cold of deep space. It's brilliant. But, does this stuff actually work in the real world? Oh yeah, this is data from field tests. In the intense sun of Phoenix, Arizona, this coating made a surface 6 degrees Celsius cooler than the air around it. And even in more humid places like New York, it still delivered significant cooling. It really works. And to put that in perspective, some of these new materials can reflect up to 99% of sunlight. That is a massive leap forward from even the best weight paints we have today, which still absorb a pretty significant chunk of the sun's heat. This kind of breakthrough, it isn't just about developing one new kind of paint. No,
This is about a whole new way of thinking about how we cool our world. What we're seeing now is the development of an entire family of these ant-inspired materials. You've got these versatile polymer paints, different nanocomposites, and even structural materials like supercool cement. Each one is being designed to bring this amazing passive cooling to all sorts of different applications.
And what's great is how practical they are. I mean, look at this. You can see one of the polymer coatings being easily applied to plastic, metal, even wood. You can spray it, you can paint it, you can put it on almost any surface you can think of. Rooftops, cars, you name it.
So what's the big picture here? What's the real-world impact? Well, just think about how much we rely on air conditioning. It's a massive drain on our electrical grids, and it ironically pumps huge amounts of heat into our cities. This technology does the exact opposite. It offers a way to cool our buildings and our infrastructure for free, with zero energy. We're talking about a way to slash energy costs, cut emissions, and fight back against that urban heat island effect that makes our cities so hot in the summer. It just leaves you with this one powerful thought. The blueprint for a cooler, more sustainable future wasn't invented in some billion-dollar lab. It was perfected over millions of years by a tiny insect running across the scorching hot sand of the Sahara, just waiting for us to finally pay attention.
Don't go anywhere, hit subscribe, and we continue.
When you picture a robot, you probably think of something rigid, right? All metal and gears, powerful, precise, and totally predictable. But here's the thing. The future of robotics, it isn't really about inventing something brand new. It's about copying a master engineer that spent millions of years perfecting a completely different design, one that, get this, doesn't have a single bone in its body. That's because the key to building robots that can actually handle our chaotic, unpredictable world, well, it isn't found in a factory, it's found in the ocean. So the real question we have to ask is, what can this boneless, soft-bodied marvel possibly teach us about engineering for the real world? All right, so to really get where we're headed, we first have to understand the limits of where we are right now. And the truth is, robotics has a pretty fundamental problem. Our machines, they're built for a predictable world, not our messy, chaotic one. I mean, think about it for a second. A factory robot. It's brilliant at doing one single repetitive task in a perfectly controlled environment. But what happens when you ask that same robot to navigate the rubble of a disaster site, or, say, perform super delicate surgery inside a human body? Yeah, that's where things just fall apart. They simply aren't designed for anything unpredictable. And this comparison right here, it really gets to the heart of the whole challenge. Traditional robots, they're brittle. The goal, the dream, is to create soft systems that are resilient and, safe to be around. Engineers are working like crazy to bridge this exact gap, basically trading all that stiff, mechanical rigidity for something much more adaptable and fluid. So how in the world do you solve a problem that fundamental? Well, the answer wasn't some newfangled alloy or faster computer chip. Nope, it was a blueprint from one of the most ancient and frankly brilliant engineers on the entire planet, the octopus. I mean, this creature is a living, breathing paradox. It has absolutely no skeleton to anchor its muscles, but it can generate incredible force. It can be so soft it can squeeze through the tiniest crack, and yet it's also precise enough to unscrew the lid from a jar. It's a complete masterclass in boneless engineering. Okay, so the secret to all this strength is a structure called a muscular hydrostat. Now I know that sounds super complex, but you actually use one every single day, your tongue. It's just like an elephant's trunk. It's basically a dense bundle of muscle that provides its own support, all because the water-filled tissue inside literally can't be compressed. And if you look inside, the structure is just ingenious. You've got this central nerve cord, and it's surrounded by a tightly packed, three-dimensional array of muscles. You have some running across the arm, others running along its length, and then you have even more that wrap around it in a helix. And that whole arrangement, that's the secret sauce. That's the source of its incredible control. And all that clever muscle work creates this beautifully simple system for movement. It's amazing. When the transverse muscles, the ones running across, squeeze, the arm gets thinner and longer. It elongates. Then, when the longitudinal muscles contract, it gets shorter and pulls back. Elongate, shorten. Just two simple actions that, when you combine them, create practically infinite possibilities. And this right here, this is that moment. This is where biology officially becomes engineering. Researchers looked at this absolutely incredible natural system and had a realization. They didn't need to build a better, rigid robot. They just needed to copy the octopus.
Okay, get a load of this. I mean, it might look biological, right? But what you're seeing is pure robotics. This is what's known as a continuum robot, and it's doing something called whole arm grasping. It's wrapping itself around an object exactly like a tentacle would. This is a direct one-to-one translation of octopus mechanics into a machine.
So unlike a traditional robot arm that has, a few distinct joints, an elbow or wrist, that kind of thing, these continuum robots have, at least in theory, infinite degrees of freedom. That means every single point along their length can bend and twist. That allows them to conform perfectly to any shape they need to grab onto or move around.
Okay, but how do you actually build one? Well, engineers are using a few really ingenious approaches. Some of them use what are called fluidic actuators, basically pumping air or liquid into flexible chambers to make it move. Others are using special shape memory alloys that bend when you heat them up, or even really intricate tendon systems that pull on tiny cables. But in every single case, the key is using soft, compliant materials, think silicone, to mimic the muscle tissue itself.
All right, so now that we've got a handle on the how, let's get to what I think is the most exciting part, the why. Why is this huge shift from rigid to soft so revolutionary?
It's because by completely abandoning rigid skeletons and joints, we're unlocking the ability to create robots that can go where no machine has ever gone before. We're literally building tools for environments that were, up until now, just too complex, too delicate, or way too dangerous for our old, brittle machines.
And the applications are just incredible. We're talking about snake-like robots that can wiggle and crawl through the rubble of an earthquake to find survivors. We're talking about surgical tools that can navigate inside the human body to reach a tumor without damaging any of the healthy tissue around it. Grippers that can gently handle fragile deep-sea creatures or even capture tumbling space debris. And yeah, even in farming, they can harvest the most delicate fruit without leaving a single bruise. In fact, let's look at a perfect real-world example right now. What you're seeing is a tendon-driven soft gripper, and it was designed specifically for harvesting blackberries. Just look at how it gently conforms to the shape of the berries. A rigid metal claw would just crush them, but this soft, octopus-inspired design, it can handle them with exactly the delicate touch that's needed. And hey, the results from the field tests, they pretty much speak for themselves. This gripper achieved an 88% detachment success rate. Now that is a powerful demonstration of how looking to nature can solve some very practical, very real-world engineering problems. What you're seeing is efficiency and gentleness, all rolled into one.
Ultimately, this is about way more than just robots. For 100 years, we've been building machines based on rigid skeletons, basically based on our own anatomy. But the octopus, it shows us a completely different and, in so many ways, a superior model. And it really forces us to ask a bigger question. What other machines have we been building the hard way when nature's soft solution was waiting there the whole time?
Don't go anywhere, hit subscribe and we continue. When we look at some of humanity's greatest challenges, it's pretty amazing how often nature has already, quietly, engineered the perfect solution millions of years ago. And today, we're going to look at one of the most elegant examples of this, our search for fresh water.
So let's meet a couple of absolute masters of survival. On the left, you've got the Namib desert beetle. And on the right, something you've probably seen 100 times, a simple spider web just covered in dew. These guys thrive in some of the most arid places on the planet, places where finding liquid water is virtually impossible. They are, without a doubt, nature's original water harvesters.
So that begs the question, right? How in the world do they pull a drink out of what seems to be nothing but bone-dry air? And the answer? Well, it's not just some cool piece of biology trivia. It might actually hold the key to solving a massive global crisis.
Because right now, today, over 2 billion people live in countries that are experiencing high water stress. I mean, just let that number sink in. That's more than a quarter of the entire world's population. Finding new, sustainable sources of water, it's not just a nice idea anymore. It is an absolute necessity for survival.
So how does nature pull this off? Let's take a look at the original water hack, something that evolution perfected long before we ever even thought to try it. And the way they do it, it's just so incredibly elegant. The Namib beetle, it literally just angles its body into the morning fog. These tiny little bumps on its back become collection points for moisture, which then conveniently rolls right down into its mouth. At the same time, you have desert plants like the Welwitschia, which spreads out this huge network of shallow roots right near the surface, designed for one thing, to soak up every last bit of moisture from fog and dew. No pumps, no power, nothing. Just pure, brilliant physics.
So naturally, we humans saw this and thought, hey,
We can do that. We decided to copy nature's playbook. And this is what you might call biomimicry version 1.0, taking a brilliant idea and scaling it up from the back of a tiny beetle to a supply for an entire village. Okay, so the concept here is just brilliant in its simplicity. You just put up a big mesh net in a really foggy area. The wind does all the heavy lifting, pushing that fog right through the net. The tiny water droplets in the fog, they cling to the mesh, they combine to make bigger drops, and then good old gravity pulls them down into a collection trough. It's a totally low-tech, zero-energy solution, and it actually works. It's an absolutely ingenious idea that provides clean water to a lot of communities. But there is a huge limitation. There's a major catch that stops it from being a truly global solution. You see, these nets are completely, 100% dependent on a very specific weather condition: dense fog. So, what do you do in the places where there isn't any fog? I mean, what about the hyper-arid deserts, where the air feels like it's been stripped of every last drop of moisture? To solve the water crisis there, we need a serious technological leap. We have to go from simply harvesting fog to harvesting the humidity that's hidden in all air, everywhere. And this, right here, is where the story takes a fascinating turn. This is where we go from just copying nature to collaborating with chemistry on a nanoscale. We're talking about a revolutionary type of material that completely changes the whole game.
This material is called a metal organic framework, or MOF for short. Now, that sounds super complex, I know, but the idea behind it is actually beautiful. Just imagine a sponge, but on a molecular level. MOFs are these incredible, programmable crystal structures engineered to have an enormous internal surface area. Get this, a single gram can have the surface area of an entire football field. And they're designed to be the perfect trap for specific molecules. In our case, water vapor.
I mean, just look at this. This is the intricate, lattice-like structure of a MOF called MOF 303. Every single one of those open spaces is like a tiny, custom-built cage, perfectly sized to attract and hold on to individual water molecules, literally pulling them right out of the air, even when the humidity is crazy low.
Okay, so let's break this down, because this is the real paradigm shift. Fog nets, they work on a big macro scale. They rely on condensation, and for that, you need high humidity. But MOF harvesters, they work on the nanoscale, using a totally different process called molecular adsorption. Think of it like a magnet for water molecules. They pull them in and hold them tight, even when they're incredibly few and far between. And this is the game changer. They can work in extremely low humidity, which suddenly opens up the driest parts of the world to water harvesting.
And that brings us to the ultimate test. I mean, it's one thing for material to work in a nice, controlled lab, but could it really pull water out of the air in one of the most famously hostile environments on the entire planet? And this is that test. Researchers from the University of California, Berkeley, took their prototype harvester, packed with that special MOF 303 material, and they set it up right in the middle of Death Valley. This isn't just some random desert. This is Death Valley, a place literally known for setting records for heat and dryness. So just how dry was it? Well, in its driest, the relative humidity during their test dropped to a shocking 9.4%. Now, for comparison, the average humidity in your house is probably between 30 and 50%. This is air that feels like it has absolutely no water in it at all.
And yet, look, success. This is that aha moment. You can see it, visible, liquid water collected right there in the vial. Here's how it worked. During the cool desert night, that MOF sponge just passively soaked up water vapor from the air. Then, during the day, the warmth of the sun was all it took to heat up the MOF and release the water it trapped. That water then condensed and dripped right into the collection vial. Pure water from desert air.
And we're not talking about just a few drops either. The results were remarkable. This new passive harvester design was able to produce up to 210 grams of water for every kilogram of MOF material, every single day. That's more than double the output of previous designs that were tested in similar conditions. It was a stunning, undeniable proof of concept. So, okay, let's step back for a second. What does a little box sitting in the desert actually mean for the future? Well, it means we may have been thinking about our water resources all wrong. This quote from the research paper really puts it all into perspective. But here's the part that most people have never heard. The amount of fresh water in the atmosphere around us is staggering. It holds nearly 6 times more water than all the world's rivers combined.
Just think about that. We've been so focused on the water we can see, the rivers, the lakes, that we've been ignoring this vast, invisible reservoir floating right above our heads. This technology gives us a way to finally tap into that atmospheric ocean anywhere on Earth with no energy input other than the sun itself. And that forces us to ask one final, mind-bending question. If we can pull fresh water directly from the air, even in the driest deserts on the planet, could the air truly be our next and most abundant ocean?
Thanks for watching. Support BioVellum by liking, subscribing, and sharing. Let's explore the secrets of nature together.